Hi, I'm Bob. We have learned the simple linear regression model, the OLS estimates, the zero conditional mean assumption, and the properties of the OLS statistics. We will solve the first 6 problems at the end of Chapter 2 today. The textbook I use is Professor Jeffrey Wooldridge's Introductory Econometrics, a Modern Approach, the 7th edition. Here's the first problem. Let kids denote the number of children born to a woman, and let edu denote years of education for the woman. A simple model relating fertility to years of education is kids equals beta 0 plus beta 1 times education plus mu, where mu is the unobserved factors. The first question is about what kinds of factors are contained in mu. Are these likely to be correlated with the level of education? We know many unobserved factors are contained in the error term mu. They include the woman's demographic characteristics such as age, race, health, and employment status. These factors affect the woman's decision to have children. Her family background also influences fertility. The unobserved factors are likely to be correlated with her education level. Take family income as an example. Women with higher family incomes have more resources to raise more children, whereas low-income families may decide to have fewer children. And family income is correlated with women's level of education because the better educated women are more likely to earn more and have wealthier families. Like family income, many unobserved factors contained in the error term are determinants of the outcome variable fertility, and they are also correlated with the explanatory variable education. The second question. With a simple regression analysis, uncover the ceteris paribus effect of education on fertility. Explain. No, a simple regression model cannot show the ceteris paribus effect of education on fertility. The ceteris paribus effect means keeping all other relevant factors equal. In other words, we must hold fixed the unobserved factors contained in the error term. The zero conditional mean assumption must be satisfied to obtain the ceteris paribus effect. However, the unobserved factors in the error term are very likely to be correlated with the explanatory variable education. The OLS estimates from simple regression analysis are biased estimates for the ceteris paribus effect. Let's go to the second problem. In the simple linear regression model, suppose that the expected value of mu is not zero. Let alpha 0 be the expected value of mu. Show that the model can always be rewritten with the same slope but a new intercept and error, where the new error term has a 0 expected value. Here's the answer. The key is adding alpha 0 and subtracting alpha 0 on the right-hand side of the equation. The new error term mu tilde equals mu minus alpha 0. So its expected value is 0. The new intercept is beta 0 plus alpha 0, but the slope is still beta 1. The third problem, the following table contains the ACT scores and the GPA for 8 college students. GPA is based on a 4-point scale and has been rounded to 1 digit after the decimal. The first question asks us to estimate the relationship between GPA and ACT using OLS. That is, to obtain the intercept and slope estimates in the equation, GPA hat equals beta hat 0 plus beta hat 1 times ACT. Comment on the direction of the relationship. Does the intercept have a useful interpretation here? Explain. How much higher is the GPA predicted to be if the ACT score increases by 5 points? I input the GPA and ACT data in Stata. I use the command regress to obtain the OLS estimates. The intercept estimate is 0.568 and the slope estimate is 0.102. The simple linear regression of GPA on ACT assumes that ACT has a ceteris paribus effect on GPA under zero conditional mean assumption. The direction of the causal relationship is assumed to be from ACT to GPA. The intercept does not have a meaningful interpretation here because it is the estimated GPA when ACT is 0. But the range of ACT is from 21 to 30, with a sample mean of 26. The slope estimate implies that if the ACT score increases by 1 point, the GPA increases by 0.102. It suggests that the GPA is 0.51 higher if the ACT score increases by 5 points. We can also compute the slope and intercept estimates by hand using the OLS estimator we have learned. We generate the sample means of x and y. Then we calculate the distance of each observation from the mean. The numerator is part of the sample covariance between x and y, and the denominator is part of the sample covariance of x. Using the formula of the slope estimate and the intercept estimate, we obtain the same results as when we use the regress command. In the second question, we need to compute each observation's fitted values and residuals and verify that the residuals approximately sum to 0. I use the Stata command predict to compute the fitted values and residuals. Here's the list of each observation's fitted value of GPA and the residual, along with the actual GPA. The fitted values and residuals are computed based on the OLS estimates of beta hat 1 and beta hat 0 and the estimated equation. We summarize the residuals mu hat and find that the sample mean is approximately 0. The t-test shows that we cannot reject the null hypothesis that the sample mean of mu hat is 0 at the 1% significance level. That is to say, the OLS residuals sum up to 0, which is the first property of the OLS statistics. The third question: what is the predictive value of GPA when ACT is 20? We put 20 into the OLS estimated equation. The predicted GPA is 2.6 when ACT is 20. The fourth question is about how much of the variation in GPA is explained by ACT. We see that the R squared in the result window, the R squared is 0.58, meaning that 58% of the variation in GPA is explained by the variation in ACT. We can also compute it by hand. R squared is equal to the explained sum of squares divided by the total sum of squares. The result is exactly the same as from the regress command. Let's solve the fourth problem. The dataset BWGHT contains data on births to women in the United States. Two variables of interest are the dependent variable, infant birth weight in ounces, and an explanatory variable, the average number of cigarettes the mother smoked per day during pregnancy. The following simple regression was estimated using data on 1,388 births. The first question is, what is the predicted birth weight when cigarette is 0? What about when cigarette is 20? Comment on the difference. When the woman does not smoke during pregnancy, the predicted infant's birth weight equals 119.77 ounces, the intercept estimate. If the woman smokes 20 cigarettes per day, the estimated birth weight is 119.77 minus 0.514 times 20, that is 109.49 ounces. The difference is 10.28 ounces. The cigarette's effect on infant birth weight is negative. On average, one more cigarette reduces the infant's birth weight by 0.514 ounces. The second question, does this simple regression necessarily capture a causal relationship between the child's birth weight and the mother's smoking habits? Explain. No, this simple regression does not necessarily capture a causal relationship between the child's birth weight and the mother's smoking habits. A causal effect of smoking on the infant birth weight can be captured if the zero conditional mean assumption is satisfied. In other words, if the unobserved factors contained in the error term are not correlated with the explanatory variable, the mother's smoking habits, then we can capture the ceteris paribus effect of the mother's smoking habits on the child's birth weight, and a causal relationship between smoking and infant birth weight can be established. However, many unobserved factors are correlated with the woman's smoking habits. These unobserved factors include age, health, educational attainment, family income, and marital status. The simple regression model could not capture causality without controlling for these factors. The third question: to predict a birth weight of 125 ounces, what would cigarettes have to be? Comment: to have a predicted birth weight of 125 ounces, or a fitted value of 125 ounces, we put 125 into the left-hand side of the estimated equation. Solving the equation, the number of cigarettes is -10. It is impossible. It happens when we use a linear regression model, but the true relationship is nonlinear. Moreover, when we look at the simple regression model and the fitted equation, we find that the highest birth weight we can estimate from the equation is 119.77 ounces when the cigarette is 0. However, in the sample, 697 out of 1,388 observations have birth weights higher than that. The simple regression model cannot fit the data well. We can also see it from an extremely low R-squared of 0.02. Here's the fourth question. The proportion of women in the sample who do not smoke while pregnant is about 0.85. Does this help reconcile your finding from part 3? About 85% of the women does not smoke during their pregnancy. There are more than 1,000 actual values of the childbirth weights for the women who did not smoke. But there is only one fitted value of 119.77 if the woman did not smoke, because the cigarette is the only explanatory variable in the simple regression model. It leads to poor fit. Next, let's do the fifth problem. In the linear consumption function, the estimated marginal propensity to consume out of income is simply the slope beta hat 1, while the average propensity to consume is as follows. We have the following equation using observations for 100 families on annual income and consumption. The first question is to interpret the intercept in this equation and comment on its sign and magnitude. The intercept is the family's annual consumption when its annual income is 0. It is minus $125. It does not make any sense for a negative consumption. The second question: what is the predicted consumption when the family income is $30,000? Putting 30,000 into the OLS estimated equation, we have the predicted consumption of $25,465. The third question asks us to draw a graph of the estimated MPC and APC with income on the x-axis. The MPC the marginal propensity to consume is the estimate of the slope parameter. It is 0.853, a constant. The APC, the average propensity to consume, is a function of income. Here are the curves for MPC and APC. Let's go to the sixth problem. Using data from 1988 for houses sold in Andover, Massachusetts, the following equation relates housing price to the distance from a recently built garbage incinerator. The first question is to interpret the coefficient on log distance. Is the sign of this estimate what you expect it to be? The estimated coefficient on log distance is 0.312. It suggests that housing price increases by 0.312% if the distance from garbage incinerator increases by 1%. That is, the housing price will increase by 31% if the distance is doubled. The longer the distance, the higher the housing price. The positive side is what we expect it to be. The second question, do you think simple regression provides an unbiased estimator of the ceteris paribus elasticity of price with respect to distance? No, the simple regression cannot provide an unbiased estimator of the ceteris paribus elasticity of housing price with respect to distance, because many relevant factors are omitted from the model. For example, whether the area is a commercial center is a determinant of the housing price. The price is usually higher in commercial areas than in rural areas. The city chooses the location of garbage incinerators based on whether it is a commercial center. It is more likely to locate the incinerators in rural areas than in commercial centers. The positive correlation between the housing price and the distance from garbage incinerators is due to the fact that both of them are related to whether the houses are in commercial centers. The OLS estimate is biased without accounting for these factors. The third question, what other factors about a house affect its price? Might these be correlated with distance from the incinerator? Other factors that affect its price include whether the house is in a wealthy neighborhood, the house size, the age of the house, and so on. They are correlated with the distance from the garbage incinerators. The above are my solutions for the first 6 problems. Hope they help. See you in the second part of the problem set. Thank you for watching this video and subscribing to my YouTube channel. See you next time.